So students, today we're going to look at another example of a 1,2 disconnection, but this time we're not going to disconnect to the epoxide, but rather disconnect to the alpha halo carbonyl compound, such as an alpha chloroketone. There's two nice things about these alpha chloroketones. Firstly, that they can easily be made from chlorination of a ketone, so it's a nice, simple, known, reliable reaction. And the second thing is that the alpha chloroketones have a very electrophilic carbon atom in the alpha carbon. The fact that the carbonyl group is directly bonded to the carbon, which is also bonded to the chlorine, makes that alpha carbon very, very electrophilic and easy for a nucleophile to attack that particular carbon. So let's jump in and have a look at that example. I'm going to use the same example from your books, so you can follow in your textbooks along with this particular example. And the molecule that we're going to look at is this particular structure. A methyl group with a carbonyl group, an alpha carbon next to the carbonyl group, and this nucleophile in this case is imidazole. So you have this particular structure, and we want to perform a retrosynthetic analysis on this particular structure. You will notice that if I look at the heteroatoms in the molecule, immediately I see a CN disconnection, which I can make. And by doing that, I will disconnect the most reactive part of my molecule, which will leave me with that synthon and that synthon. The synthetic equivalence for this will be easy to do. All I need to do here is put a hydrogen and a nitrogen with a negative charge. And for this particular ketone structure, I put a halogen next to the alpha carbon. If I put a halogen next to the alpha carbon, I now have a very nucleophilic, very electrophilic carbon atom, which a nucleophile can easily attach to. So looking at the synthesis of this particular molecule, I can start off by using a ketone in my synthesis, which I can easily chlorinate with CO2 and acetic acid. And once I chlorinate my naphthalene molecule, I can now add in the nucleophile to this electrophilic center and get my desired product. There's a carbonyl group, the alpha carbon, to which the imidazole is attached. I take a quick look at my structure to see that I have all my carbon atoms intact, and you can see if I started off with a naphthalene structure and a carbonyl group, I have a naphthalene structure and a carbonyl group in my molecule. My alpha carbon is there and my imidazole is there as well. I haven't lost any carbon atoms along the way. I used this carbon backbone in my first step, and all I did was activate this carbon atom so that the nucleophile, which in this case was imidazole, can attach to that electrophilic center and give us the resultant product. So the two nice things about this, to repeat, is that these alpha chloroketones are very nice because they can easily be made in this particular reaction. So it's a known reliable reaction where we can make this. And secondly, this alpha carbon now becomes very, very electrophilic in that the nucleophile can easily attach, and it's so electrophilic because we have an electronegative chlorine atom here and electronegative carbonyl oxygen here, both withdrawing electron density from that particular carbon atom. I hope you enjoyed watching the video. Watch this space for more.